All right, we're starting here with an inverse function. And essentially what we're looking for is a function that undoes another function. So the idea is if we have a function here, f of x, say this is this is our function machine where we give it a bunch of materials to make breakfast, right? It's our breakfast machine, breakfast. And it takes in all the, you give it the eggs, you give it the sausage and bacon or whatever, and it makes you some sort of, you give it flour and stuff, and it makes you some sort of biscuit sandwich or something. And then it's essentially what we have to have is a machine that then takes that biscuit sandwich, right? And it basically undoes the breakfast. So if this was our breakfast, we're going to indicate it with a little -1 in the exponent like this. What it's going to do is output, it's going to take our biscuit sandwich or whatever, and it's going to break it back apart into the eggs and whatever else and the flour and stuff like that that we use to make it. So basically, it's something that gets, we have our function that puts something together, it does some sort of action, and then we're going to have a function here, so f of x, and then we're going to have a function here which will indicate with a little -1 there that's going to undo it. So if we give it a 7 and it outputs a 10, then we feed that 10 into our inverse, it's going to give us back a 7. It's something like that. It's going to make sure that those two things turn out to be the same. It's going to undo what the original function did. So what is an inverse function? It's the function that does the opposite of what was there. So if we have a function here, f, let's say, for example, it's the square root of x, where we give it a value and it takes the square root of it. Our inverse function is going to do the opposite of that. And the opposite of a square root is squaring it. So if I take something like 9 and I give it to the function for the square root and it square roots it and gives me 3, I can then give it to the square function, the inverse function, and it'll square it back and give me the 9. So if it was like that, I would say I have square root, I give it 9, it outputs 3. I then put that 3 into x squared, which is the inverse of it, and it outputs 9. And again, I end up back to with what I started at the beginning. So it's kind of just a function that undoes what the other function does. Another example of this could be if we have something plus 10, if we add 10, how do we undo that? Well, we take 10 away. So if I give you $10 and then take $10 away from you, one was me giving you 10, the other was me taking it away, you end up with the exact same amount that you had before it all. The inverse of something like 2x, if we had a function 2x, its inverse would be x divided by 2. Because if we multiply something by 2 and then we divide it by 2, we end up with getting back exactly what we had before. We denote this function with just a little -1, and that actually comes from the idea of a negative exponent. So like if I have something like 7 to the -1, if you know this means 1/7, okay? Here, that doesn't mean this. F to the -1 does not mean 1 over it. All right, what we're using it for is to indicate inverse, not, excuse me, inverse, not necessarily reciprocal. When we're talking about just a number, that -1 means reciprocal. When we're talking about a function, it means inverse function. Now, in some cases, it is just the reciprocal, kind of like right here. But in other cases, it is not just taking a reciprocal. It depends on what you're doing. You have to figure out the inverse of whatever the operations that are occurring are. All right, so let's take a look here. One of the things that turns out to be true here, of course, is that whatever our input is, whatever we input, let me do that in green, whatever we input will be what we get back as the output for a function if they are. And so what we can actually do is just plug in one function into the other and see if it just essentially gives us back just an x. So in other words, what I mean by that is we're going to do this right here. If we just have two functions, we could go in and we could pick a single value. Like I could say f of 7 equals 7 minus 10. And then I would take that and say, all right, that's -3. And then I could go along and say, all right, let me plug -3 in. And I get -3 plus 10 for g of x. -3 plus 10 is 7. And I'd say, oh, hey, that works. But doing it that way only tells me that it works in that one situation. It doesn't tell me that it actually works in every situation that we would come across. So we don't want to do that. We don't want to just pick a single number and check it, because we might just get unlucky and happen to pick a number where it seems like it works, but then it doesn't work for any other numbers. So the way we want to do it is we actually want to do what we have right here. We want to plug one function into the other and see what happens. And so if we do that, if we plug one function into the other, we get f of g of x is equal to f of x plus 10, right? We're plugging in x plus 10 for g of x right here. So we replace that g of x with x plus 10. And then inside of f of x right there, we're going to replace that x with x plus 10. So it'll be x plus 10 and then minus 10 like that. And if you notice, when we do that, we end up with just x. And so by doing that, we got just x. That means that no matter what value for x we used, any number we pick, we're going to end up right back where we started with whatever it had. And therefore, those are inverses of each other. And in fact, we can do number 2 here where we reverse it and we do g of f of x like that, which is g of, what was f of x? X minus 10, which equals g is x plus 10, so it becomes x minus 10 in place of x, and then our plus 10, and this again just equals x. So if you plug one inside, right, you do this composite function like this of the two functions, and you end up just getting x as a result, what this tells you is that they are inverses of each other. All right, if they were not inverses of each other, you'd end up with something that wasn't equal to just x, and we'll see that at some point here as we go along. So let me pause and see if we have any questions at this point. All right, let's take a look here and see what we can observe about this relationship where we have f of x equals x minus 10 and the f inverse of x equals x plus 10. So if we try plugging in values like this, so let's say we start off and we plug in 10. We do f of 10 equals 10 minus 10, which equals 0. If I then take that 0 and move it across to here and plug that 0 in there, I do f inverse of 0 equals 0 plus 10, and I get back out the 10. And the thing you should notice is this, the same, because these two functions are actually inverses of each other. Let's try another number. Let's try, I don't know, let's try 12. All right, we plug 12 in. F of 12 equals 12 minus 10, which is 2. If I then take that 2 and plug it in over here as the input for the other one, I get 2. And so I have the inverse function evaluated at 2. And that's going to be 2 plus 10. And I get 12. And again, you should notice here, this 12, that 12, they're the same. So these two are most definitely inverses of each other. And we could go in and plug one into the other and see that that is true, but we don't need to do that at the moment. So what I want to do here is take a look at this next page. So like we just did where we did the composite functions, I just did it right here for f of g of x and g of f of x in these two examples, and I ended up getting x. What I'd like you to do is go ahead and try that on this page. I want you to try plugging them in. So in other words, what you're going to do here for number 3 is you're going to do f of g of x and see what you get. And then you're also going to do g of f of x, all right, and see what you get. Test it both ways and make sure that they both turn out to get it. So we're going to check to see if the composition of the functions equals x. In other words, that's what we're checking. If they equal x, then they are inverses of each other. If they do not, then they are not inverses of each other. So go ahead and start giving those ones a try. All right, here, so showing you number 3 here. I already started and plugged in and did the first one here where I did f of g of x, and I plugged in x minus 2 for g of x, and so then I substituted in x minus 2 over 3 for x there. So this was my 3x plus 2 right there, but with that substituted in. Anyway, after doing that, it's just a matter of going through and trying to reduce this. I see that I have 3 and then a divided by 3 there. So these two are going to cancel, which will just give me x minus 2 and then plus 2. And I have minus 2 plus 2. Those will cancel to give me a 0, and this will just equal an x. So right there, that looks pretty good. Now let's try it the other way. We're going to plug f of x inside of g of x. So this becomes g of, and instead of f of x, I'm going to write 3x plus 2, because that's what f of x was. And then here, I'm going to take right here where this x is, and I'm going to write 3x plus 2. Then I'm going to finish off with the minus 2 and the divided by 0. So minus 2 divided by 0, that part right there. Okay, so that's what I substituted out. Now it's a matter of going through and trying to reduce this. I have 3x plus 2 and minus 2. So those plus 2 and minus 2 are going to cancel. And it'll leave me with 3x over 3. The 3's will then cancel, and I'm left with just x. So you can see here, both ways that I did it, I ended up getting just x. So they are inverses. All right, because they both turned out to be x. All right, go ahead and try number 4 now and see if you think it turns out to be inverses. All right, so after these, we found some inverses and some not inverses. Let's take a look here at what is called the horizontal line test. What we can do is we have to check and see if a function is one-to-one. And we do this by what is called the horizontal line test, because it turns out it's kind of like the vertical line test, but with a horizontal line. We need it to only hit once. It turns out if we do the inverse of a function, like this function here is f of x, this is like e to the x, its inverse function here is shown here in blue. So let me grab blue. This is f inverse of x is actually just the natural log of x, because natural logs undo exponentials. And then we have right across here along the middle, we have this dotted line. This is just y equals x. This is our identity function, f of x equals x right there. And if you notice, they are like mirror images of each other. If we took and folded along that dotted line of y equals x, they would line up right on top of each other. Okay? And so if you want to know if a function has an inverse function, not just an inverse, but an actual inverse function, then what we can do is actually check the original function using the horizontal line test. Just like the vertical line test, but we're looking to see if horizontal lines hit it more than once. As we can see here on our function f of x equals e to the x, the horizontal lines are only hitting it once, which means if you go through and after you do the inverse, you do the vertical line test, it means our inverse function will then pass the vertical line test. So if the original function passes the horizontal line test, it will then have an inverse that passes the vertical line test. So looking at this, I say, yes, all right, it has an inverse because it passes, sorry, it has an inverse function, not just an inverse, has an inverse function. Yes, because it passes the horizontal line test. All right, take a look at this other one. If we look at this one over here, my original function here is f of x equals x squared. And if I try my horizontal line test on it, look, it fails it. It hits it in 2 places. It fails the horizontal line test, which means if once I do the inverse, I don't have a function because the vertical line test, this inverse function here, is not a function. So it fails that. Again, notice though that along this dotted line, we could fold it right along that dotted line and they would match up. They're like mirror images across that dotted line. But you can see that it failed the horizontal line test, which means the inverse will fail the vertical line test. So this is a no. It fails the horizontal line test. Okay? So if a function does pass the horizontal line test, it's called one-to-one and therefore has an inverse function. If it fails it, the original function can actually be a function, but its inverse function will not be a function. It'll just be an inverse, not an actual function like you see there in the second picture. So what we mean is one-to-one means every input has a separate output. So this, if I have 2 inputs, if this is my input and this is my output, and I have 2 inputs that are leading to the same output, it's a function, but it's not one-to-one. And therefore, that function wouldn't have an inverse function. However, if I have something like this, where this is my in, this is my output, and each input maps over to its own unique output, then we have what is a one-to-one function. And you have to have a one-to-one function in order to have an inverse function. And so a one-to-one function is the only type of function that has an inverse function. We need to say that. It's an inverse function. And so the inverse function of the graph is reflected about the line y equals x, as we saw in these pictures up here, where it's just like this is a mirror and it mirror images it and reflects it across that. You simply end up swapping every xy value. So if I go here and I see I have the point 0, 2, I come down here on this graph and I have the point 2, 0. I swap all the x and y values and it will do that. All right, so let me pause here and see if we have any questions. All right, and then the final thing here we have to do is actually finding an inverse function if we're given a function. And the way we do this is we basically just follow these steps right here. First thing is you have to check and see if the function is one-to-one. So in other words, you have to make sure that it passes that horizontal line test like we just did on the previous page. So you have to think about what the graph looks like and see if it passes that test. If it does pass the test, then you move on to steps 2 through 5. You replace f of x with y in the equation. Then you swap. Everywhere you have an x, you write a y, and everywhere you have a y, you replace it with an x, and then you solve again for y. All right? If it does have that inverse, then you've essentially found it. Replace y by the f inverse symbol. So let me show you on this one. So I look at f of x equals 3x minus 5. This is simply a straight line. It goes through x is negative 5 and has a slope of 3. So the graph looks like that. It therefore is a straight line and passes the horizontal line test. So the first thing I see is step 1. Yes, it passes that horizontal line test. Therefore, I can move on. Step 2 says replace f of x with y. So I'm going to write this as y equals 3x minus 5. Step 3 says swap all the x's and y's. So I'm going to write this as x instead of y equals 3y minus 5. So I just swapped the x's and y's. Everywhere there was a y, I made it an x. Everywhere there's an x, you make it a y. And then we have to solve for y. So we start with this and we start solving for y. So I add 5 to both sides and then divide both sides by 3. Okay, that gives me y equals x plus 5 over 3. And then step 5 is replace that y, since we know from step 1 we do have an inverse function, with f negative 1 equals x plus 5 over 3. And therefore, by doing that, we have found the inverse function for that right there. If you wanted to, then at that point, you could try doing the composition to make sure that it actually did work. But if you did the composition of this, you would find that they are inverses of each other. So let me go ahead and do one more. Let's look at x squared plus 2 right there. If we look at the x squared plus 2, right, we do step 1. Does it pass the horizontal line test? So what does this graph look like? Well, if we look at this graph, the graph looks like this. It's a parabola, right? It's that x squared graph, something like that. Well, if I try my horizontal line test, it fails it, right? Fails that horizontal line test. This was at plus 2, so this should have been down here. All right, it fails the horizontal line test, and so therefore I can stop. You know, it fails it. Fails the horizontal line test, and so I stop. There's no inverse function. Therefore, no inverse function. And I can just stop right there, okay? If I try one like number 10, you would find that it does pass the horizontal line test because this graph looks like this. And if we do the horizontal line test, it will pass it. So step number 1 is passed, which means you can start moving on to steps 2, 3, 4, and 5 to find that inverse. Okay, so go ahead and take the rest of this time and try finishing working out numbers 8 and 10.